I promised I'd talk to you a little bit about batteries, and this is going to be part of how I discuss that. I'll also discuss it in class a little bit later, but how does a battery actually work? Well, let's imagine we have our little battery. There we go. Be the positive end, and this will be the negative end. Okay, what's actually going in the battery? Many people think that batteries store charge, which is actually not true. Our whole language is actually based around that. We talk about batteries, which is part of the problem. We talk about a battery discharging, losing its charge. We need a fully charged, rechargeable batteries. It's unfortunate language. What's really going on in a battery is you have two different ends that have different metals in them typically. I'm going to, I know, get confused and not remember which end is which in a standard battery. So please don't quote these metals as being correct. But an example would be zinc and copper. Zinc and copper have different electronegativities. When you react with some kind of chemical, like an acid, one of them will have a higher affinity for attracting electrons, and the other one will be left attracting more of the positive charges that are left. Okay? In other words, the electrons will go maybe to the copper, and then what's left, say the hydrogen plus ions, will go over to the zinc. You can do this in different ways, but it's often done with an acid in between. Your car battery typically, I believe, has sulfuric acid, if I remember right. I can't remember what's in your standard dry cell battery you put in most of your devices. Modern batteries, batteries and hybrids used to be lead batteries. Now they've got lithium. Lithium has its own interesting way of dealing with this same situation, by the way, that I'm not going to explicitly get into, but it's conceptually similar. Okay, so what happens as this reaction happens? Well, every time you have one of the positive charges going this way and a negative charge go this way, just like with a capacitor, you're setting up an electric field like this, okay? Every single time a reaction happens, you set up an electric field. It gets stronger, okay? Now, eventually this has to stop. The reason this has to stop is every single subsequent charge, pair of charges that try to move in this now growing field have to fight the field. The positive charges do not want to move upfield. So eventually, their propensity, their desire to react with the positive terminal of the battery is overcome by this electric field, and that's where the whole reaction stops. Now, this reaction stops at some very specific voltage. That's the voltage where it would take more energy for the positive charge to move upfield than it would release chemically by reacting over there. Okay? That's a very definite amount of energy per charge. It's a very definite voltage. Okay? That is why your battery produces a fairly specific voltage. A little bit later, we're going to meet what real batteries look like, and it turns out there's a slight variation in the voltage due to, depending on the current, rather, that flows through them. We're not going to discuss that for a while yet, though. So this is where the battery sits when it's just sitting in the open, okay? If I put a wire across the batteries, the terminals rather, maybe a resistor on there so it doesn't discharge immediately, current starts to flow. So positive charges leave the positive terminal and go around the negative terminal, okay? But every time some positive charges leave the positive terminal, that reduces the electric field, okay? Reducing the field inside the battery means, oh, hey, there's a bunch of charges now that will gain more energy chemically by moving up to the positive terminal than they will have to lose by fighting their way up this field, okay? And so they go back and they react and restore this field, okay? This is why batteries produce very stable voltages, okay, even when they're being used. Now, it is, I suppose, theoretically possible to discharge a battery so quickly that it's had the charges flow so rapidly out of the ends and around to the other side that the chemistry can't keep up. Okay, I can envision, for instance, a superconducting wire, no resistance at all. Okay, and in that case, the charges would move so fast that I can envision a time when the battery just cannot chemically react fast enough. Okay, chemistry does happen quickly, but it takes a finite time. But that said, that's really not easy to engineer, at least not in my thought experiment. So typically you have a very stable voltage until something happens. That something is this reactant in the middle is eventually going to run out. Okay, it's just all going to have reacted with the zinc and with the copper on the ends. You won't have any more stuff in the battery to produce this voltage where this energy is coming from, and the battery just dies. Okay. Now, it is possible to run a current backwards through a battery, okay, under certain conditions. Your standard battery doesn't really allow for this, although in theory, you ought to be able to set it up so that it would. But there are batteries that let you run a current backwards, so you force the current across the battery, okay, and that actually reverses the chemistry. By pumping in positive charges to the positive terminal, you're basically reversing the chemistry on that end. Those charges then go back into the solution in the middle here, okay, and they also pull some of the electrons off of the other end, and you end up with a rechargeable battery. That's the way a rechargeable battery basically works. It just reverses the chemistry inside the battery. Now, in theory, it's always reversible, like I said, but you can't always do it efficiently or easily. So don't put your standard off-the-shelf non-rechargeable batteries in a charger, of course. However, it should be noted, even rechargeable batteries break down. Remember entropy, our old friend? Every single time you run this reaction, you're having a little bit of entropy introduced into the system, and that means you don't ever fully recharge back up to where you were initially, the very first time. So you're losing a little bit to degradation every single time. Eventually, this is just a mess. The battery, rechargeable battery, won't hold a quote-unquote charge for very long, and it's useless. Okay, but this is how batteries work. You notice the big thing, again and again and again, I keep saying, is they maintain a constant voltage, okay, across the terminals. The reason why they do that is chemistry. Okay, it's not holding charge or anything like that. It's actually chemistry. Okay. So again, the most important thing to remember about batteries, they hold their voltage. I cannot say that enough. I will say it again more in class, and I look forward to seeing everybody tomorrow.